Okay, let me continue another example about the limit at infinity. Limit x approaches infinity 6 times e to the 4x minus e to the minus 2x over 8 times e to the 4x minus e to the 2x plus 3 times e to the minus x. Okay, and for this example, the basic concept involved in working this problem is the same as with the rational expressions in the previous sections. Okay, and then now we'll look at the denominator and determine the exponential function with the largest exponent, of course. And we will then factor out from both numerator and denominator, and we'll use the same reasoning as we did with the previous lectures example to determine the largest exponent, of course. And in this case, since we are looking at a limit at plus infinity, we only look at exponentials with positive exponents. Okay, so we will factor e to the 4x out of both the numerator and denominator, and once that is done, we can cancel the e to the 4x and then take the limit of the remaining terms, and let me do that. Okay, and so limit x approaches to infinity. Okay, e to the 4x. Okay, factor out, and the parenthesis, it will be 6 minus, okay, e to the, okay, minus 6x, okay, over e to the 4x times 8 minus e to the minus 2x plus 3 times e to the minus 5x. Okay, and after that we can cancel this part of the limit, and after that limit x approaches infinity. Okay, 6 minus e to the minus 6x x over, I'm sorry, eight minus e to the minus 2x plus 3 times e to the minus 5x. Okay, and after that, when x approaches to infinity, okay, at the numerator part 6 minus 0 over, and at the denominator part 8 minus 0 minus 0, so it's equal to 6 over 8, so it's equal to 3 over 4. And let me continue with another example. Evaluate each of the following limits x approaches to 0 from right hand side ln x, and the limit x approaches to infinity, okay, and it's ln x, okay, and the As with the previous examples, we will leave it to you to verify these statements, okay, restatements from the basic logarithm sections, okay, and I will write only its result, okay, and don't forget it's equal to, from right hand side, ln x, it equals to minus infinity, okay, and for this limit x equals to infinity, ln x it equals to infinity. And note that we had to do a right-handed limit for the first one limit, okay, which is the x equals to 0 from right hand side, and we can't plug negative x's into a logarithm, don't forget it, and this means that the normal limit won't exist, since we must look at the axes from both sides of the point in question, and axes to left of 0 are negative, okay. And now let me give you another examples about the logarithm function. Evaluate each of the following limits, and the part A, limit x equals infinity ln of 7x cubed minus x squared plus 1, and the part B, limit x equals to minus infinity, okay, ln of 1 over x squared minus 5x. Solution. Let's first look to see what the argument of logarithm is doing, okay, and it will say us firstly limit x equals to infinity, okay, and the argument, which is the 7x cubed minus x squared plus 1, okay, and it will be infinity, right? And the argument of the logarithm is going to infinity, as you see, and so the logarithm must also be going to infinity in the limit, okay? So the answer to this part is then we will find that limit x equals to infinity ln of 7x cubed minus x squared plus 1. We know that it's the infinity, so it's equal to infinity. Okay, and the part B, what was part B? Yes, x equals to minus infinity. So the firstly, okay, note that the limit going to negative infinity, okay, don't forget it. And here isn't a violation, okay, unnecessarily of course, and this isn't a violation of the fact that we can't plug negative numbers into the logarithm, okay. And the real issue is whether or not the argument of the logarithm will be negative or not, okay. So using the techniques, okay, and the limit x equals to minus infinity, the argument part 1 over x squared minus 5x, so it's equal to 0, right? And the argument of the limit is 0. So what will we do? We will do, okay, and it's the minus infinity in the limit, so the numerator will always be positive, and so the quotient will always be positive. Therefore, not only does the argument go to 0, okay, it goes to 0 from the right. That means it goes to 0 from the right. So this is exactly what we need to do this limit. So that means limit x equals to minus infinity, okay, and the ln 1 over x squared minus 5x is equal to minus infinity. Okay, that's important. Okay, and then let's continue with the some trigonometric functions. Okay, and the part E, let me write them. Evaluate each of the following limits, of course, and the part B, and it will be enough, I think. Maybe part C. Okay, okay, and the first one is limit x equals to infinity inverse tangent x, or another name is arctangent x. Okay, and the second one is limit x equals to infinity, I'm sorry, it's not infinity, it's minus infinity, inverse tangent x, and the last one is the limit x equals infinity, okay, inverse tangent of x cube minus 5x plus 6. Okay, let's evaluate all of them. Solutions. And the first two parts of the example are really just the basic limits involving inverse tangents and can easily be found by examining the following, which I will sketch the inverse tangent function. Okay, and the remaining two parts are more involved, but the last one was more involved, but as with the exponential and logarithm limits, really just refer back to the two first parts, which I will sketch it. Okay, and then let me sketch it. The inverse tangent functions. Okay, and this graph has the horizontally asymptote at the pi over 2 and the minus pi over 2. Okay, and the okay, pi over 2, and then this is minus pi over 2, and then this function is inverse tangent x. So for the part A, okay, please remember when x equals to infinity, okay, as you see, when x equals to infinity, okay, you will see our functions will go to the plus pi over 2. Okay, so the x equals to infinity inverse tangent x equals to pi over 2. Okay, and the part B, okay, when you look at it, you will see the limit x equals to minus infinity inverse tangent x. As you see, when it equals to the minus infinity, okay, you will see our functions will goes to the minus pi over 2. Okay, and the last part of, the question. Yes. Okay, in part A above, and we saw that if the argument of the inverse tangent functions, okay, goes to plus infinity, then we know the value of the limit. Okay, in this case, using the techniques from the previous section, okay, and we will have the limit x equals to, okay, infinity, okay, and the x cube minus 5x, right, plus 6, okay, and it's equal to infinity. Okay, so this limit is, okay, and the limit x equals to infinity, okay, inverse tangent x cube minus 5x plus 6, and this part will be infinity, so inverse tangent infinity, okay, it equals to pi over 2. This is the last part about that limit at infinity section. Okay, and then now let me continue with the last part of your limit section, which is about the continuity. Over the last few sections, we have been using the term nice enough to define those functions that we could evaluate limits by just evaluating the function at the point in question. Okay, and it's now time to formally define what we mean by nice enough. Okay, so let me write the definition about continuity. Okay, a function f of x is said to be continuous at x equals a if limit x equals to a, f of a equals to f of a. A function is said to be continuous on the interval a comma b close interval if it is continuous at each point in the interval. Okay, and this definition can be turned around into this fact. Okay, and the fact 1 if f of x is continuous at x equals a, then limit x equals to a. Oops, I'm sorry, this part must be, I think, a little wrong. This part is f of x, okay. F of x equals to f of a, and the limit x equals to a from left hand side, f of x equals to f of a, and of course limit x equals to a from right hand side, f of x equals to f of a. Okay, and what can we say about that fact? Okay, and this is exactly the same fact that we first put down back when we started looking at limits, which with the exception that we have replaced the phrase of nice enough with continuous. Okay, and it's nice to finally know what we mean by nice enough. However, the definition doesn't really tell us just what it means for a function to be continuous. Let's take a look at an example to help us understand just what it means for a function to be continuous. Okay, and let me give this example. Given the graph of f of x shown below, and determine if f of x is continuous at x equals to -2, x equals to 0, and x equals 3. Okay. And it's the x and y. Okay. And let's write some values. Okay, and this is the -2 plus 2. Okay, this is plus 2 values. This is 3 over 2. And at this point is -2, okay, and this is the -1, okay, and answer the question for each point, and we will need to get both the limit at the point. Okay, and so if they are equal, the function is continuous at the point, and if they aren't equal, the function isn't continuous at the point. First, let me look at the x equals to 2, x equals to -2, okay? And we know that f of minus 2 equals to 2, okay, but the limit x approaches to minus 2, okay, f of x doesn't exist. Why? Because when you approach to the, okay, this is minus 2, this is minus 1, 1, 2, this is 3, 4, okay, when you approach to the minus 2 from the right hand side, okay, your limit will be minus 1, but when you approach to the, okay, minus 2 from the left hand side, your limit will be 2. So two sides are not equal to each other, so we can say the limit does not exist. So the function value and the limit aren't the same, and so the function is not continuous at this point, okay, and we can call a jump discontinuity, okay. This is discontinuity at the x equals to 0 point, okay, and what can we say about it? I'm sorry, and for this point f of 0 equals to, okay, 3 over 2, right, and the limit x approaches to, okay, 0, f of x equals to, as you see, when you approach to 0 from right hand side and left hand side, you will obtain the same value, so your limit is 3 over 2. So we can say this function is continuous at x equals 0 point, and another point which was the x equals to 3, okay, and the f of 3 equals to minus 1, and the limit x approaches to 3, okay, f of equals, and we will call this discontinuity, okay, and this, it's the special case, okay, and we will call it jump discontinuity, okay. And the jump discontinuities occur where the graph has a break in it, as the graph does, okay. As you see, here is a jump, okay, from here to here, as you see, jump, okay. And the last one, yes, at the x equals to 3 point, okay, when you approach to the 3 from left hand side and right hand side, your limit will be 0, but the, okay, f of 3 equals to minus 1, and the function is not continuous. This is discontinuity at the x equals to 3, and this kind of discontinuity is called a removable discontinuity. Why? Okay, look at the graph. Removable discontinuities are those where there is a hole in the graph, as there is in this case. As you see, there is a hole, okay. So